Okay, so if you're anything like me, the first time I was presented with this reaction, I was really confused about why you have, or why you would ever have A as a major and B was a minor. And I really wanted to know why there would be any preference whatsoever, because it seems like the two molecules are pretty much the same. There's a little bit of a difference in location of the atoms, but other than that, they look virtually identical. What we're going to do is we're going to talk about the mechanism, and hopefully that'll help rationalize why A is a major and why B is a minor. So let's redraw the starting material, and we're going to have our starting material reacting with Br2. And the mechanism for the halohydrin begins in the exact same fashion as just regular Br2 addition. So this is good practice for the first part of the mechanism. So go ahead and pause the video, see if you can recreate the first part of the bromonium ion formation. Okay, so I've done the first part of the Br2 mechanism, and I've added some color just to make sure that we can coordinate what is forming a new bond and what is breaking an old bond. And what we would get is another bromonium ion. This purple arrow is indicating that electrons within this pi bond, within this double bond, specifically let's just choose some like this part of the double bond right there. The electrons that were being used for this bond are being shifted around, and they're now being used to make a new bond to the bromine, and these blue lone pairs on the bromine are being used to make this new bromine to carbon blue bond. Okay, and so then after this, what we are going to have left over is a little bit of Br minus and a little bit of H2O, or a lot of bit of H2O in solutions. So now what we have here is a little bit of a game of choosing what's going to be the nucleophile. So this is obviously our electrophile from the previous video, but now we have to wonder about, well, we actually have two potential nucleophiles in this solution. We have Br minus, which was our old nucleophile for just the regular Br2 mechanism. But now that we have water, and a lot of water in solution, these water molecules also have a lone pair that could, act as nucleophiles, or could be used for a nucleophilic attack. So really, in this case, either or could potentially be used, but the rationale for this mechanism and this reaction is that just by sheer numbers, the water is going to be able to overpower Br minus as a nucleophile, and it's going to be more likely to attack. Okay, so the rationale here is, what you can take is that because of this excess, the excess allows us to utilize water as a nucleophile instead of the Br minus. So we're not going to use the Br minus for this nucleophile. Okay, just keeping in mind what we want to use. Okay, so now that we have our water in solution, and we want to use that as a nucleophile, we actually have two potential carbons that we could attack. We could potentially attack carbon 1, or we could potentially attack carbon 2. And so now if you compare and contrast this product A and this product B, we can actually rationalize how we could get either one of these products by what carbon is being attacked by our water. So let's say if these electrons, these green electrons, attacked carbon 2, then we'd be forming a bond between the oxygen and carbon 2, and then that would give us product A. But if, on the other hand, these green electrons attacked carbon 1, we'd be making a new bond between the oxygen and carbon 1, and that would give us product B. And I'm going to go through both of these possibilities. So we have the one possibility, which is these electrons could either attack carbon 2, and if that happens, we'll end up getting our original molecule that now has oxygen attached to carbon 2. This oxygen is going to be positive, because remember, at this point we've only shown a bond making between this oxygen and this carbon 2. And now that we've done this first error, hopefully it's obvious that I've made a mistake here, and the mistake is that I've made a bond in this above mechanism, but I haven't broken a bond. So the bond that we have to break to keep us from having a Texas carbon on carbon 2 is going to be this purple bond right here. So I've made that bond, and so that means that I need to break this old bond right there. And then that means we're going to have carbon 1 right there. So we've got our purple electrons that came from that old bond. They're going to the bromine. We've still got our blue 1 to bromine bond. And now we're forming our new oxygen to carbon 2, so there's our green right there. And so at this point, all we really have to do is take, some other water in solution. So OH2, this has another lone pair that we can use as a base, and we can get rid of this hydrogen pretty easily. And so at the end of the day, what we formed really is, some extra acid in solution. Okay, so overall, this would be the one product. So this would be carbon 1, I think, in our old notation, and that's carbon 2. And so that explains why we get the oxygen on carbon 2. So then let's do the exact same thing, and let's just go through the second possibility. So this would be possibility B, the yellow possibility, which instead of that oxygen attacking 2, that oxygen can attack 1. And again, I've made a mistake, which is I've made a bond, but I haven't broken a bond. So good. Hopefully at this point, if you make a bond, you break a bond, that should be pretty ingrained into your thought process. So if you make a bond, you have to break a bond. So I'm going to break this bond right here, this blue bond. And so now this just means that that purple bond is still there, because this purple bond was only broken in this A process, which was up above. So A and A. And so now in the B process, the bond that's broken is the blue. So we're making a bond with the yellow, which is right there, and we're breaking that old blue bond. And those blue electrons are going to go on to the bromine as a lone pair. And so just the exact same thing as we did before. To get the final neutral product, we have to have water coming in and attacking, and we can remove either one of these hydrogens. It doesn't really matter which one we remove. And so now we can see how in this scenario, in the B scenario, the B mechanism, we can get that hydroxy on carbon 1 instead of carbon 2. Okay? So this is the mechanism as to how we actually get the two products, how we get the two major products. But we still haven't explained the why we get one as a major and one as a minor. But this is the first step, just kind of understanding how we could potentially get either one of these products. So in the next video, we'll talk about a little bit about why we actually get one as a major